This is a lesson on entropy in the heat and thermodynamics unit. In the few prior lessons, we had looked at the second law of thermodynamics and focused on it in terms of energy transfer, where we had a hot reservoir and a cold reservoir, and we looked at hot heat moving from the hot reservoir to the cold reservoir. But as we went through the interpretations of the second law, we saw that it wasn't just concerned with temperature and heat flow from a hot to cold. I started talking about disorder, or the amount of microstates available, the amount of energy states available for each particle. And you may have been getting this intuition. There must have been a more powerful quantity to encapsulate the idea of the second law of thermodynamics than just heat flow. This quantity is entropy. Entropy describes the measure of disorder in a state. And so when we're thinking about states, there's an initial state and a final state, and we measure how much disorder is in the initial state and how much disorder is in the final state. And when we look at this, an example would be ice melting to water. In the initial state, the water molecules are very ordered in the ice crystal. But when they melt, there's heat being added to the system. All of these molecules gain kinetic energy, and there's more disorder. There's more random motion. There's more states of energy for these molecules to be in. So a higher number of microstates available, the higher the entropy. So conceptually, that's what we're looking at. Entropy is equivalent to disorder, and this quantity measures the disorder. We have a quantification of the disorder of a system. As we look at entropy, we care more about the change in entropy between two states. We're comparing the entropy of these two states. The second law says that entropy will either stay constant or increase due to any spontaneous process. This is consistent with heat flowing from hot to cold. It is just now a representation of the second law in terms of entropy rather than heat. Quantifying entropy requires counting number of microstates. Entropy is defined as the amount of disorder, so to measure this, we look at the number of arrangements available in a macro state, and that's what this W is in here. W is the number of microstates available corresponding to a given macro state. I am not going to pursue calculating that for this unit. If you would like to study this further, you may look at upper division or graduate classes. I introduced this slide because I want you to see that entropy can be quantified as a state function, and you can have the initial entropy and the final entropy. It depends on the Boltzmann constant and the natural log of the microstates available, which you can count. The last thing we're going to note is units on entropy are joules per unit Kelvin. Like I said, we're more interested in the transfer of heat and thus the change in entropy. So when we look at moving from state 1 to state 2, we look at the heat being transferred in that situation. The second law of thermodynamics says heat must have transferred from a hot reservoir to a cold reservoir. We have an increase in entropy, or at the least it stayed the same. That's what the second law says. So how do I quantify this change in entropy? I take the heat transferred and divide by the temperature of the state. So whatever the state is, that's the temperature. So when I look at the symbols in here, delta S is the difference in entropy from initial state to final state. Q is the heat involved in the process, and remember this could be a plus or minus sign. So watch your signs here when you have heat involved. And then the temperature under here is the absolute temperature of a system. For this unit, for basic learning algebra-based physics, we're not going to do anything fancy here. And what we're going to assume is that each of these states is at a constant temperature. And so the heat transferred out of state 1 will happen at the temperature T1, and the energy transferred into state 2 will happen at the temperature T2. So that's the temperature that goes down here, the absolute temperature of the system that is either losing the heat or gaining the heat. If heat is added or removed from a solid or liquid corresponding to a change in temperature, we can use this equation down here, mass times the specific heat times the natural log of T final over T initial. So that's different than the first one. The first equation you use, and it's ideal for systems at constant temperature, which we will deal with mostly. You may see problems that emphasize using a change in temperature definition of change in entropy. You'll be indicated this because there will be a change in temperature of the material, and you will be looking for given a specific heat. So when we're looking at changes in entropy, we're looking at heat transfer in or out of a system. And so I think it's important to look at the different types of systems and what are the confinements of heat being transferred in or out of that system, and how does entropy play in there. Isolated systems means that no matter or energy can enter or leave a system, which means whatever heat transferred from one object in the system gets received by the other object in the system, and entropy will increase in that system. Entropy has to increase in that system for a spontaneous process, and we know that for an isolated system. However, if the system is open such that the energy transferred or any matter could be into the system or out of the system, and we're including the surroundings in it, then more forms of energy are possible and the system could do work or have work done on it. So we're getting an energy exchange with the surroundings. And so an implication of this open system for the second law is that energy must be exchanged with the surroundings in order to maintain an increase in entropy in the whole universe. So when we look at the total entropy change of the universe during a process for an open system, we have to consider whatever is inside that system that we're particularly interested in, and whatever exchange of heat that system has, typically heat, that system has with its surroundings. And I have an example of this in our problem. Now that we know we need to be aware of change in entropy of a system and its surroundings, we can look at change in entropy and how that relates to reversible processes. For a total change of entropy, and this means the system and the surroundings, if that is zero, if the entropy is constant, then that's a reversible process. No work was put into it in order to cause it to happen. There may have been an entropy shift in the system such that there's non-zero terms, but overall, the total is zero. If the change in entropy was greater than zero, which means that there was some sort of net energy put into the system, that's an irreversible process. That's something that the work was put in, we cannot get the work back out, and it can't be undone. So a reversible process is the one in which the system and surroundings can be returned to exactly the states they were before the process occurred. And what I'm going to note here, and this may come up in questions, that all spontaneous processes are irreversible. We get some work out of them. Remember, with the second law of thermodynamics, we have Q hot, which gets transferred into some work plus Q cold. If there's some sort of work lost out of it, it's irreversible. There's no way we can collect that work back and make that state to be the same as the original. And so that's an irreversible process. All spontaneous processes are irreversible, which also means non-spontaneous processes, and this should make sense to you. If it's non-spontaneous, we have to put energy, we have to put work into it for it to happen. So when you're looking at terminology, be careful about reversible and irreversible, and it's not the same as spontaneous and non-spontaneous. All of those have very specific definitions. I chose an example for us that is going to let us see how the total entropy is related to the entropy change of each individual component of the system and the surroundings. In this situation, there's 25 grams of water that condenses on a steamy bathroom mirror at a temperature of 35 degrees Celsius. It says, what is the change in entropy assuming no change in temperature assuming no change in temperature, so we can use this equation here. And given the latent heat of vaporization to be, okay, so we have latent heat. I know latent heat. When I see latent heat, I know we're condensing. That's the latent heat of vaporization. And so Q from vaporization has to equal the mass times the latent heat of vaporization. And that is going to be the Q that we use in this equation here. That'll be the vaporization. When I look at the situation, there's a mirror, and then there's water on the mirror, which I'll go like this, okay? So for me, the system is going to be the water molecules. They are losing heat. They are becoming more ordered to become a liquid. And so then surroundings is going to be the mirror, which will be collecting the heat. And that's important because we have conservation of energy. Energy needs to be accounted for. If the water is losing heat, we need to know where that heat is going. So in this situation, we're doing a simple sort of example where the heat is going to the mirror. Of course, the water is condensing onto the mirror, and the mirror is collecting that heat. Okay, so for part A, it says, what is the change in entropy of the water? So I'm just doing delta S of the water, H2O. It is losing heat. It's losing this amount of heat, the heat of vaporization. So I'm going to go negative M LV divided by the temperature, and I'm going to want that in Kelvin. It's in Celsius right now. So I'm going to plug in some numbers. The mass of the water is 0.025 kilograms. The latent heat of vaporization is 2450 times 10 to the third joules per kilogram. I'm going to put this in joules. Entropy is in joules per Kelvin. So I have joules on top, and then on the bottom, I'm going to do 35 plus 273. When I run this through the calculator, the change in entropy for the water is negative 199 joules per Kelvin. Again, it's a negative value because the water is losing heat and becoming more disordered. Part B asks, what, if any, entropy changes did the surroundings experience? In this situation, we've defined the surroundings as the mirror. So when I look at the mirror, I can say delta S for the mirror equals, well, it gains this energy, MLV, and it's at the same temperature. So the mirror has gained the energy, and I know the value, 199 joules per Kelvin, and this is a positive value. I wanted to take a second and talk about enthalpy with respect to entropy. Enthalpy, if you are familiar, is delta H, and it's defined as the heat required for a chemical process to occur at constant pressure. So this can be represented as Q sub P for constant pressure, heat at constant pressure. And it has unit joules. Notice that enthalpy has unit joules. Entropy, however, has units joules per unit Kelvin, and it represents disorder. So they're not the same quantity, they're not the same concept at all. And we're also going to note that enthalpy is the same at any temperature. Regardless of temperature, the amount of heat required for a chemical process to happen at that pressure is a constant value. However, entropy depends on temperature, and adding heat at lower temperatures has more of an impact in creating disorder than at higher temperatures. And this is a concept that we've seen before, but is one of those important ones about entropy, is that temperature matters. How many microstates are available? When we're at a low temperature, there's much more microstates available for a system than if the temperature is high and all of those microstates have been occupied already. Enthalpy is the same at any temperature. The energy it takes to have a chemical reaction happen is the same. In order to relate enthalpy into the concepts that we've been talking about, because it is an energy term, it fits in with conservation of energy, and this is the right way to put it in there. For any chemical process, energy must not only go into breaking or making bonds, but also for making room for the products. So H is defined as enthalpy The change in enthalpy will equal the change in the chemical energy. Remember, this is the energy that goes into breaking or making chemical bonds. So that's the chemical energy. And then this is the work done by the substance in making room for the products. And if you are in chemistry, you may use this equation, and that's how entropy and enthalpy sound like they should relate to one another, but they don't.